Welcome to sample injection. A good technique called sandwich injection when you're injecting the sample into the gas chromatograph is illustrated here. So first you draw in air, so that's the portion over here. Then you draw in some solvent, then you draw in some more air, and then you draw in your sample, followed by some more air. And this way, when the needle is inserted into the injection port, there's no sample here in the needle itself. If some sample were residing in that needle when it gets pushed into the injection port, it would then vaporize prior to the plunger being depressed, thereby spreading the sample band out even prior to arriving on the column. The air that's between the sample and the solvent prevents them from mixing. And that solvent plug then washes any residual sample that's left behind in the needle. And that final air plug pushes the solvent from the needle, so there's no solvent left inside the needle. So here we have a schematic of an injection port. The cyanized glass liner, which is here, this portion there. That cyanized glass liner prevents our solutes from interacting with the heated metal walls. The heated metal walls are this darker gray here of the injection port. Now the carrier gas transports the vaporized sample from the injection port over here into the column, which goes out then this way. If analytes are at high concentration, so this is greater than about 0.1% or so, then split injection is preferred. For high resolution, the smallest detectable amount sample should be used. And typical sample volumes are below 1 microliter, and the samples contain less than 1 nanogram of each component. Large sample volumes will overload the column with a diameter of 0.32 millimeters or less. And with split injection, only around 0.2 to 2% of the injected sample actually makes it onto the column, and the rest is discarded to waste. The sample should be injected rapidly, so under 1 second, through that septum, and is then quickly vaporized in the high temperature of the injection port. And a high flow of carrier gas flowing this way and down that cyanized glass liner transports the sample to the mixing chamber, which is here. And then that sample gets carried on to the split point, so the sample either goes this direction onto the column, or it goes that direction out to waste. At the split point then, a small fraction of our sample flows to the chromatography column here, and the remainder then exits to waste via this needle valve 2 there. Note that needle valve 1 was over here going to a vent. So the pressure regulator leading to needle valve 2, so that's this pressure regulator here, controls the fraction of sample that is discarded. The split ratio is the ratio of sample discarded to sample passed to the chromatography column, and the split ratio is generally between about 50 to 1 and 600 to 1. Now once the sample has been flushed from the injection port, that's at around 30 seconds, then the needle valve 2 over here is closed and the carrier gas flow is reduced. One downside to our split injection, not slit injection, this is split injection, is that the split ratio is not reproducible from run to run. And that means that quantitative analysis may be inaccurate. You're going to need an internal standard with every run that you do. So suppose that 1 microliter of a liquid sample is injected. Upon vaporizing, that sample volume is around half a milliliter. And the rapid expansion of sample upon vaporization may cause some of the vapor to be expelled out the hole in the septum. Now, because the low boiling point components will vaporize faster than the high boiling point components will, the low boiling point components may be preferentially expelled through that hole in the septum. So, the temperature of the injection port should be high enough to minimize this fractionation of the sample, so we want to keep the temperature around 350 degrees Celsius. However, if the temperature is too high, then the solutes can decompose in the injection port. During injection and chromatography, the septum purge gas flows through needle valve 1 at around 1 milliliter per minute to remove excess sample vapor and gas bleeding from that hot rubber septum. Now with trace analysis of analytes with concentrations below 0.01%, then splitless injection is used. A similar injection port as that used in split injection is used, but there is no mixing chamber. And a large volume, so around 2 microliters of sample in a low boiling point solvent is injected slowly, so this is around 2 seconds. And that split vent is kept closed. The septum purge flow is kept slow during the injection and chromatography to remove vapors that escape that injection liner. And because the septum purge flow is low and no gas is vented to waste via needle valve 2, then around 80% of the injected sample actually reaches the column. Now, that low flow rate of carrier gas of around 1 milliliter per minute means that the sample is in that glass liner for around 1 minute. Now, because the sample spends more time in the injection port during splitless injection than in split injection, the temperature in that injection port must be lower. It must be kept low enough in order to prevent decomposition, so generally around 220 degrees C. The initial column temperature is around 40 degrees below the boiling point of the solvent. And thus, the solvent condenses at the beginning of the column in a plug. And as the solute then arrives at the solvent plug, it dissolves in the solvent. And this creates a narrow band of our solute at the beginning of the column. And this process is called solvent trapping and gives us a much sharper chromatographic peak than if the solvent were not condensed. Without solvent trapping, the peaks would be at least as wide as the residence time in the injection port, so around 1 minute wide. Chromatography then proceeds when the column temperature is raised to vaporize that solvent that's trapped at the beginning of the column, and that means that then it releases all those solutes to travel down the column. So instead of using solvent trapping, we could use cold trapping. In cold trapping, the initial column temperature is around 150 degrees lower than the boiling points of the solutes of interest. So the solvent and low boiling point components will be eluted very rapidly, but the high boiling point components will remain in a narrow band at the beginning of the column. And chromatography then proceeds when the column temperature is raised, just like with solvent trapping. And this figure shows how altering the operating parameters will affect the chromatogram. So we've got 4 different chromatograms here, A, B, C, and D. Chromatogram A uses split injection with a split vent open, and the column is at 75 degrees C. And note here, we've got some very nice sharp peaks. In chromatogram B here, we have the same conditions as A, except that the split vent is closed. And note here that we've got some significant tailing on each of our peaks. They're still coming out at exactly the same times because it's the same column, same carrier gas, same flow rate. But now the peaks here are tailing much, much more than they were there with the split injection. And this is occurring because the sample was applied to the column over a very long period of time due to the slow purge of the injection port. That purge gas continually mixes with our sample in the injection port, which dilutes the sample, but it never effectively purges it from the port. Also note that the peak area in B is much higher than the peak area there in A, because a higher fraction of the sample is reaching the column in B than it is in A, because we threw away most of our sample in A with a split injection. With the split vent closed, we're keeping most of our sample, and that's getting onto the column then. So now here in chromatogram C, we've got the same conditions as in B there, except the split vent was opened after 30 seconds. And so note here the truncation of each of our peaks after 30 seconds. The chromatogram is otherwise the same as what we have in B. And now in chromatogram D, here we have the same as in C, except the column was initially at 25 degrees C in order to trap the solvent. And so note then we've got these nice sharp solute peaks similar to what we had in A, except the peak areas here are larger than in A because we got more of our solute onto the column in D than we did in A. Also, note that the scale in D here must be multiplied by 2.33 to be the same as in from A to C. That is, that solute peak areas in D are much larger than they were in A. So most of our sample is reaching the column in chromatogram D here, but whereas only a small fraction of our sample is reaching the column in chromatogram A. So for quantitative analysis and for samples that decompose above their boiling points, on-column injection is the preferred method. In this case, the sample is injected directly onto the column without passing through an injection port. The initial column temperature is low enough to condense the solute in a narrow band. And chromatography then proceeds when the column temperature is raised, just like in cold trapping or solvent trapping. And that was sample injection.